Hi, I'm Ben Shapiro, and I'm an assistant professor of computer science at the University of Colorado Boulder, and I'm going to be speaking to you today about emerging paradigms for CS education and what the implications of those could be for visual programming languages. I want to begin by acknowledging the students that I have the pleasure of working with every day. Together, we are the Laboratory for Playful Computation, and our collective mission is to design and study experiences and technologies that empower young people to learn through creative play, expression, and problem solving. I'm going to lean pretty heavily on Rebecca Fiebrink's work in parts of this talk, so I also want to acknowledge her right up front as well. This talk's got 5 parts. First, I'm going to talk about what computing, that is computer science and computing education, were like yesterday and what they're like today. I'll talk about theories of what computer science is yesterday and what they might be tomorrow. I'll then delve into design research that my students and I have been doing to explore what contemporary computing education could be like. I'll use that to critique what we think is missing from today's tools, and then I'll give some design research suggestions for researchers on visual languages and human-centered computing. So to start, I want to talk about the practice of computer science and computer science education as it was practiced yesterday and as it's practiced today. And to do that, I want to begin by going back in time, specifically to 1985. In 1985, the ways that we used computers in our daily lives were really different. Most people didn't use graphical user interfaces yet. The Nintendo came out in the US that year, and the internet was just getting off the ground. Very few people used network computers. This was also the time when key theory about concurrent and distributed systems was being developed. In short, consumer computing technology was in its infancy, and networking was quite rare. Now, if we fast forward to today, things look really different. We all have mobiles, some of us have wearables, we might have Internet of Things type devices in our homes and communities. We regularly use social computing systems like Twitter or Facebook, maybe Snapchat, and we might even have Bluetooth connected technologies for animal-computer interaction. When we look across these types of technologies, we can see some trends in what computing is today. For one thing, it's heavily networked. It also quite often involves concurrency or distributed systems. It's heterogeneous. We use lots of different kinds of technologies together. It's ubiquitous, and we use different kinds of interfaces to support that, like speech or tangible interfaces. It's also quite statistical. Machine learning powers many of the technologies that we use every day. And it's also more open than ever before. Many of the kinds of technologies that we use that interoperate with one another weren't actually made by the same people. That's a sort of practical view of what are computing tools today. Now let's look at computer science education as it was in the past and how it is now. 30 years ago, we were in the first CS education boom, and Logo was a key technology for that. The programming language Logo revolved around loops, conditionals, and simple graphics, and it was a great way to engage with the PCs that we had at the time. These were von Neumann machines with some memory, some graphics, a keyboard, and support for local I/O, like making sound. If we fast forward to today, we see that actually much of the stuff that's out there in terms of programming tools for beginners is roughly the same content repackaged. In fact, this is an example from right off of Google's site, but other sites like code.org have quite similar stuff. And when we juxtapose these, we see that the biggest difference between the programming tools and the programming paradigms that kids have today and the ones that they had 30 years ago is that today they're prettier, they're better at preventing syntax errors, and sometimes they include features for sharing work with other kids. But unfortunately, the basic computational ideas reflected in these approaches to learning are unchanged. The field of computer science has moved forward, but our learning tools for computer science education generally have not. Right now, we're giving kids educational tools for yesterday's computer science. The truth is that the most popular tools that are out there for learning to code do not reflect how many of the technologies that we use today actually work. Nor do they let young people construct the kinds of technologies that they're passionate users of every day. My students and I believe that we need programmable tools for beginners that authentically reflect the computer science of today, with all the rich, ubiquitous, networked interaction that I mentioned before. Now, those are some concrete differences between CS and CS education in the past and how it is today. And now I want to get just a little bit more theoretical. What do we even mean when we say computer science? Well, Aho and Ullman have said that computer science is the science of abstraction, that it's about creating the right model for a problem and designing the appropriate mechanizable techniques to solve it. They're talking about abstractions and models, representations of problem domains, and the construction of algorithms to work with those abstractions. Abelson and Sussman have argued that programs must be written for people to read and only incidentally for machines to execute. I interpret this as meaning that we should be able to understand the semantics of the programs that we write, as well as the relationships between the inner workings of those programs and the problems that they're meant to solve. Now, if both of these definitions are true, then the essence of computer science is fundamentally epistemological. It's a field focused on building formal and human comprehensible representations of information about problems. Sometimes negative definitions are helpful as well. Hal Abelson has said that computer science is not about computers in the same sense that physics is not really about particle accelerators and biology is not about microscopes and petri dishes. Hal's point is that in defining computer science, we shouldn't confuse our tools with the intellectual pursuits, the knowledge that we're building within the discipline. Now, it's become popular in education discussions around computing to talk about something called computational thinking. Well, based on the definitions of CS that we just heard, we might define computational thinking as thinking with and about abstractions. And indeed, this logic is at the core of how Jeanette Wing has described computational thinking, as being about abstractions and automations. Some commentators have emphasized algorithms a bit more than abstraction, Perlis talking about algorithmizing or Papert talking about procedural thinking, but in both cases it's about human formulated solutions and structured solutions to human understood problems. These definitions of what computer science and computational thinking are have made sense for a very long time. But the argument that I want to make now is that they make less sense now than they used to, and that they will make even less sense in the future. Here's why. Current definitions of computational thinking break down in a machine learning era because they cannot account for the knowledge that's contained in networks like these. There's knowledge embedded in the edge weights and the activation thresholds of every element of these neural nets, but this knowledge is rarely human comprehensible. We typically don't understand whatever the abstractions are that are captured by these networks. Yet, we wouldn't say that someone applying machine learning to solve a problem isn't thinking computationally. Therefore, we need theories of computational thinking that can resolve this paradox, that can account for the rich computational thinking of working with systems like this. In short, we need to work towards more expansive definitions of what computer science and computational thinking are, in order to account for things like machine learning. The truth is that computer science is no longer just a science of human comprehensible abstractions. It's now a hybrid of that and statistical utilitarianism, and CS education needs to grow to include the utilitarian, statistical approaches of machine learning, in addition to the abstract formalisms that have long been the core of the field. In a few minutes, I'm going to talk about how we might create visual editors that help people to grapple with this complexity by helping them to weave together symbolic abstractions alongside and in an integration with statistical models. Current approaches to CS education also don't account very well for the highly distributed nature of contemporary computing. The abstractions and automations used in distributed programs aren't the same as in single-threaded programs running on von Neumann machines. But not a single published K-12 focused CS education framework, standards document, or curriculum asks for students to be able to reason about distributed systems, to design network protocols, or to do other things that build on this model of computing. ACM and IEEE's 2013 undergraduate curriculum treats these as elective topics as well. And I think this is quite problematic. We need computing education experiences that embrace these ideas and others from the computer science of today and where the field is heading tomorrow. After all, every piece of technology up here, and these are all things that are in use today, involves distributed systems, and most include some kind of machine learning model as well. In our group's work, we've been trying to develop pathways for beginning programmers that embrace these ideas from contemporary computing. Specifically, we seek to understand what it could be like for introductory computer science to include distributed computing and machine learning. And that's what I'm going to talk about now. Some design research from my lab. And in particular, I'm going to talk about two lines of research. The first is about middle schoolers designing and building distributed systems. And the second is some reflections on a university course I've taught on machine learning for HCI. I'm going to start with distributed systems because we've spent several of the past years designing tools and experiences where young people, ages 10 and up, design and program their own distributed systems. This work started with computer music, but since then it's progressed to other genres of computing system. Well, first I want to define what I mean by distributed computing or distributed systems. One way to think about this is that distributed computing is lots of programs working together to perform a computation. Typically, when people refer to distributed computing, they're referring to these lots of programs running on different computers connected with each other over a network. Now, this is a really important paradigm for computing because it lets us build all kinds of new types of applications, ranging from mobile apps that collect data about the acceleration of your car in order to inform real-time traffic models and systems like Waze, to online games, banking systems, and just about any other high-scale computing system today. The challenge with this model is that things break and there's much more uncertainty about what's happening. Networks introduce information propagation delays, and the different programs that cooperate in distributed systems operate independently. They don't execute in lockstep, and it can be hard to design algorithms that work within this computational model. In addition to these timing issues, there's also the challenge that you may not know when parts of a system have failed, and so algorithms need to be designed to be robust in light of the fact that some nodes in a system may just disappear and you may not know that they are dead. As I mentioned, in distributed systems, we don't always know the total ordering of operations within a system. There is no global linear ordering in distributed systems. We can know about the sequence of instructions within one program running on one device, but we can't know that in total across the whole system of nodes working together in a system. And the way you get correct outputs out of a system with this kind of stochasticity is through the design of robust communications protocols. In our work, we've operationalized this with an important design implication, which is that protocol design for robust coordination between programs, including the handling of time and failure, is a critical computational thinking practice for a distributed computing world. And based on this, we came up with two research questions. First, how do we get kids started doing this kind of work, designing distributed systems and the protocols to construct them? And then what does computational thinking look like in this space? We hypothesized early on that music could be a very powerful way to get people started in distributed computing. And our approach is that young people would work together in teams to design and build their own computer music instruments. They would program those instruments, and then they would use them to perform in groups. And what I mean here by instrument is some sort of interactive musical technology. Why computer music? Well, most kids love music. They know about it. They want to talk about it. Sometimes they want to dance to it. And the cultures and communities that they come from give them knowledge of different genres of music and different structures of performing music. These are all things that we can draw on in rich ways in the classroom. Another nice property of music is that it has both parallelism and distribution. Most music has chords. A chord is when two notes are played at the same time. If that's happening on the same instrument, we can think of that as parallelism. But when we look across a group of performers, we can think about them having to manage distributed concurrency to be able to do multiple things at the same time in time with one another. Many pieces don't sound good if this distributed concurrency falls apart. Many people also have knowledge of different kinds of performance structures where humans have to do this kind of organization with one another. And it might involve central orchestration or more subtle distributed head cues and other knowledge to support collaboration. A band and an orchestra can note different mechanisms for doing this. A band is typically a bit more distributed and peer-to-peer than an orchestra is, which always has a centralized timekeeper. In thinking about this, we came up with a small set of computational ideas that we use to drive our design of learning experiences. The first is that networks are collections of communicating nodes, and that each node in a network is an independent computer that can run one or more programs. Each one of those programs is a process, and each one of those processes is a sequence of operations that happens one at a time. Now, when you have multiple programs having to work together, this opens up opportunities for learners to bump into problems with synchronization, race conditions, and other challenges of coordination in distributed systems. The way we built on these ideas to design a learning experience and a set of learning technologies is as follows. Our Blocky-Talkie project is all about creating learning experiences and technologies that embody the goals I just described. Kids using Blocky-Talkie design and build physical devices that each run independent programs. And these programs, or these devices if you care to think of it that way, they each communicate with each other over the network. Here's a very simple example. It's a device with one button, and this particular device is configured to use a Lego sensor button. But generally, student projects working with us have involved different kinds of sensors, including buttons, knobs, sliders, distance sensors, temperature and humidity, pretty much anything you can think of. And they program these devices to respond to these inputs and communicate with each other over the network. Typically, when we go into a classroom, we bring buckets of these devices, and each one has a unique name, such as Bubbles or Wonka. And the programming model is that students can pretty easily write code to send messages between devices. Here's an example of code from Bubbles to send a message to Wonka, and an example of a program on Wonka to handle the receipt of such a message by starting to loop a melody. This is an example of what the technical structure of a musical project involving 3 devices can be like. In this case, we have a device with a button sending messages to 2 synthesizer devices to start the rhythm and melody elements of a song. As I mentioned, time is different in distributed programs, and students working in the Blocky-Talkie music paradigm have to account for this. Time in Blocky-Talkie, like in distributed systems generally, is partially ordered. And by default, our synthesizers play sounds immediately. As soon as you give it a play instruction, it will play. And this would be fine if students had perfect timing and ability to coordinate with each other, and if the system was latency-free. But neither of these characteristics is true, and it requires students to do work to accomplish synchronization. And to support that accomplishment of synchronization, we provide a 2-part programmable mechanism to construct synchronization. First, students can configure devices to subscribe to clock update messages from other devices. By default, each device sort of has its own internal metronome, but you can program a Blocky-Talkie device to subscribe to the clock from another device. And that way you have a common sense of what time it is. Next, once students do that, they can write code to make their synthesizers wait for specific timing announcements, such as the downbeat in a piece of musical timing. The effect of this combination is that if 2 or n devices are subscribed to the same clock and also wait for the same beat to occur, then they can play music in sync with one another. This is what it's like. That was the design of Blocky-Talkie. Here's what it's like when we go into classrooms. We do our research largely in school classrooms in the school day, and part of our process is to co-design instructional units with teachers that they will implement in their classes with some support from us. These units are generally around 12 to 20 hours of class time, and we collect multiple kinds of data along the way, including audio, video, code, survey, and interview data. Here are some photos from one class, a public middle school music class where students had substantial music theory knowledge. So they were building on their musical knowledge in order to create these interactive computer music instruments to use in group performance. Along the way, they created blueprints of what they wanted to make, including what the musical performance structure and user interfaces would be. And they often used their instruments and sheet music to try out musical elements before actually programming them with code. So you see an example of this in the bottom left with students holding a violin and a flute as they're trying out musical ideas before programming them. The students worked with representations like this NFA in order to compose harmonies that match the melodies that they made. This NFA captures the rules for classical chorales. Students wrote music and then programmed different devices to play pieces of that music in response to user input. And they used tools like this NFA to do things like figure out the harmony parts to melodies that they had designed. Some of our quantitative data enable us to see how students' projects evolve, such as how the kids invent ideas from networking and distributed systems as they're working on their programs. These network graphs are of one group's project over time. So here are graphs from 4 different days of a project. We generated these by programmatically rendering the connections between programs through parsing students' code save files. So every time students press save, we have a time-stepped copy of their program. And at the end of each day, we scraped that code to understand clock subscriptions and message sending between all of the programs that constituted a project. These are the first 4 days of a Coldplay mashup project. Here's 2 more days. And this is the final project. The network structure and the details of students' programming are content that we analyze in our work. And we study their code to understand the computational richness, including network structure, of individual projects, as well as to look across projects to understand the variation in students' ideas and implementations. When we look across different students' projects, we can see quite different network topologies, and we can even detect specific kinds of bugs just from these diagrams. For example, in the cornhole game, we see that 2 devices keeping time are mutually subscribed to one another, and it's not clear what the behavior of this system should be over time. Our qualitative data give us windows into the social processes through which students construct these systems. We've frequently seen them disagree about how to distribute work within a system, or wrestle with how to define protocols that abstract away implementation detail. Unfortunately, I don't have time today to play video for you of students' conversations, but a journal article about some of these findings should come out next year. We're just doing final revisions on it. Now, we've been working towards scaling up our tools to run across different kinds of hardware to support a wider variety of projects. As I mentioned earlier, the tools we use today run on quite different kinds of platforms, and these systems pictured here have quite different degrees of processing power, memory, energy requirements and heat dissipation, network connectivity, size and weight, sense of belonging to an individual or possibly being a collective technology, as well as their sensing and actuation capabilities. Over the past year, we've been working on scaling up the walkie-talkie model to work across different types of hardware from these different types of platforms. So we now have working support for devices like the BBC microbit, which you can use to make wearables and other compact, low-power, battery-powered technologies. We've always supported the Raspberry Pi, and we now also enable kids to be able to build mobile apps that talk to these other platforms through extensions to MIT App Inventor. This summer, we'll release a walkie-talkie cloud that also lets students write persistent programs that run on a cloud server at the university and that can send data to and from their various devices. In August, we piloted the use of some of these tools in summer computer science programs for middle school girls. So far, we're very excited about what we're seeing. For example, one group made this step-counting dog collar that lights up when the dog meets activity goals. They made a mobile app for setting and monitoring those goals, as well as for customizing the lighting. And these devices communicate back and forth with updates to configuration or updates to information about how far a dog has walked. So as we've gone from computer music to things like IoT devices and smart dog collars, we've come up with some observations that I'd like to share. The first is that messaging has been remarkably easy for students to understand. Asynchronous messaging between devices that communicate over a network in order to build more complicated systems out of simple programs. Frankly, we've not seen any deep challenges with students understanding the fundamental idea of asynchronous communication between programs. Typically, we introduce it by analogy to texting, so instead of you and a friend texting each other, two programs text each other. Or sometimes we make a comparison to yelling to a friend across a playground. The last one is useful because it sort of brings up issues of reliability. So your friend might or might not hear you, but you can expect that they'll hear what you say in the order that you say it. And that's like the guarantees that we've built into the system. Our students have been very curious about the ways in which asynchronous messaging protocols can support interesting interactions between programs. And we've seen things like prank wars, where groups of students will pull up the code to other groups' projects and then start sending spoof messages to the other group's devices just to see what can happen when things go awry with the protocols of a program. We believe that this kind of transgressive play could offer the beginnings of a really rich approach to cybersecurity education, and that's a direction we hope to go in the future. However, students often have to do considerable work to understand the causes of bugs in distributed programs. Distributed state is hard to inspect, it's hard to reason about, and protocol violations can be tricky for students to detect. Sometimes students expect a message A, but receive a message B, and they don't always know why. We know that we need better representations of the system state, of protocol flows, and of problems like unhandled messages, and that's stuff we plan to address in future work. Overall, we think we're still quite early in this research, and there's lots more work we need to do to get it right. In a few minutes, I'll talk about where we think some of this research could go. First, I want to talk about machine learning. Earlier, I talked about the misfit of current computational thinking theories and CS education approaches with distributed systems and machine learning. Here I'm going to drill down a little bit on machine learning. I don't have to explain to computer science audiences how deeply machine learning is changing computer science, both within academia and within the practice of industry. But I still want to provide a little bit of framing around machine learning that can support the last part of this talk. In general, we can think of many interactive technologies as having this kind of block diagram. Some sort of sensors or a network provide input, which gets fed to some sort of algorithm, which then controls some sort of output or actuation system. We can think of the middle block in this diagram, the processing and decision-making block, as a function that maps from input to output and possibly maintains some state. Well, we can also think about building and using machine learning systems as being about the data-driven construction of functions and then the application of those functions. What I mean by that is we use data and algorithms to train models. Machine learning models are the product of machine learning algorithms. Those trained models are functions, and training them is a process of empirical function construction. Then, once we have those models, we can apply them to new data at runtime to make inferences. An approach that I'm very excited about exploring in educational contexts is called interactive machine learning. And a key distinction between interactive machine learning and machine learning in general is that in interactive machine learning, humans are in the loop to edit training data as well as to make changes to modeling algorithms and feature extraction systems. A nice affordance of interactive machine learning is that artistic and human interaction goals can be used to shape data over time in order to improve the quality or reliability of models. In interactive machine learning, we modify our data sets to make model construction easier. For example, we might change hand gestures so that it's easier for a computer to reliably distinguish them. But we might be constrained in doing so by our artistic or other aesthetic goals. There may be gestures we don't think would be appropriate. And so we're bounded on one side by our aesthetic goals, and we're bounded on the other side by the machine learning algorithms. I've been wanting to learn more about what it could be like for people to learn about machine learning, and in particular interactive machine learning. So last spring, I taught a university course on interactive machine learning for HCI. The structure of this class was that it was divided roughly in half. The first half was a flipped class where my students used Rebecca Feebrink's MOOC and did short small group projects and then we used class time to discuss and troubleshoot their products. The second half of the class was a large group engineering project, large in terms of time. It was an 8-week project, and groups typically had 3 to 6 students in them. In these projects, they were tasked with building an interactive system that would either enhance creative expression or assist somebody with a disability, or both. And their final project had to have an embedded machine learning engine in it so that end users could customize the system that they built. One of my favorite projects was called Noodlebot. And the premise of this project was to create a soft robotic tentacle that might be attached to the back of a wheelchair so that somebody who's paralyzed could still control this tentacle with nerve impulses, such as by thinking about what they want it to do. In the end, their tentacle was able to point at things, touch things, and even had a grabber at the end in order to pick things up. This project took quite a bit of work for the students, and they had to combine mechanical and electrical engineering with computer science. At the core of all of this was a machine learning model to interpret data from wearable sensors and to make mappings between those nerve sensors and what the tentacle should do. We used Rebecca Fiebrink's Wekinator throughout the class, and the interactive machine learning loop that it affords was hugely helpful to the students. Here's what it's like to build machine learning models with her tools. Rebecca has built tools that enable students to not only train models, but to inspect the models as they've been constructed. And my students found this quite helpful when trying to understand the ways that different kinds of machine learning algorithms can represent differently distributed data sets. Imagine we want to understand how different classification algorithms work, or how those algorithms perform with some training data that we've created. Well, here's a training data set. Each data point has 2 attributes, which are depicted here as X and Y values. We're doing supervised learning, and the colors here are the labels of the supervision. So there's some red data, blue data, green data, and yellow label data. We can feed these data to different classifier learning algorithms, and then with Rebecca's tools, we can use Monte Carlo methods to generate visualizations of the boundaries that these algorithms learn. So here's what a decision tree trained on these data look like. Here's an ADA-boosted version. This is a support vector machine version. And here's k-nearest neighbors with a k of 1. These generated models have strikingly different boundaries, and we can quickly get a sense of how they perform with new data given our training data. All of the lighter, less dense data points are new data that are simulated data, and we can see where these fit in the different boundaries that the models have learned. And then we can use that information to make choices about how to edit our training set to improve performance. In a sense, this is a view into the knowledge that the machine learning model has developed through its examination of our training data. When I see this, I wonder, is this abstraction? Is this automation? Are these even the right categories to think about this? To be an abstraction in the sense that Aho or Abelson or Wing talk about, I should be able to name the parts of the model and talk about their relationships in a sense that isn't extremely tied to the concrete details of my data. But in looking at this, I don't have a way to name one squiggle or another, and they don't necessarily correspond to any abstraction that I have in my head. Furthermore, if I add or take away a data point, the squiggles can move quite dramatically. To me, that doesn't seem like abstraction. But there's still something here that is a representation of my data. And the squiggles do represent some sort of abstract representation of the space. Impressionistic might be the right word. An impressionistic version of the contours of my data set, if not a perfectly abstract one. Now, I've shown you examples now of our work on young people programming simple distributed computing systems, and I've also shown you some of the tooling that Rebecca has developed to make machine learning more accessible. Well, what does this have to do with visual languages for programming and learning? Through doing some of this work, I've come to see some gaps in how we're building visual programming tools, especially tools intended for beginners. I think those gaps are interesting, and I also think they suggest some productive research directions, and I want to talk about those now. This brings us to the next part of my talk, which is reflections on our experiences so far. Now, there are numerous different types of visual programming language, but clearly imperative programming with blocks has succeeded in engaging beginners at a scale far more massive than any other approach. There are now many, many tools that use blocks to help programmers to get started in computer science. We just had the second Blocks and Beyond workshop that was fully focused on blocks and CS education. As David Weintraub has pointed out, block-based editors offer programmers quite useful structure editing help. They prevent most kinds of syntax errors, but they also provide other kinds of resources for people learning programming. Most of us who build blocks-based editors owe a huge amount of thanks to Neil Fraser and the Google Blockly team. Neil's the leader of that team, which has produced this block editing toolkit from Google, which is used in many tools, including App Inventor, Code.org's tools, MakeCode, and the BBC Microbit, as well as the tools we build in my lab. I'm super excited about the ubiquity of these tools and the ways they're making programming more accessible. But as happy as I am about all that, I'm also quite frustrated. I think we should be disappointed by the state of these tools. The truth is that blocks are pretty boring, and that's because they aren't any more expressive than text. They also rarely are implemented in ways that do all they could to actually help programmers. Most uses of blocks today and beginner-friendly tools are to prevent syntax errors. They're very often, if not always, implemented as graphical overlays over textual languages, and typically they are near perfect isomorphisms for that text. Blockly lets one very quickly bring up a blocks-based editor that can generate textual code for an existing language. And if you're using a toolkit like Blockly, you don't need to touch anything further down the stack. Blockly is language and runtime agnostic because it's a unidirectional code generator. There is no runtime or compiler that can do deeper analyses of a program. Right out of the box, one can go from these blocks to a whole bunch of output languages. This is another example that isn't Blockly, but it's a great example of isomorphism. The representation of a web page on the right isn't any semantically richer than the text on the left that it encapsulates. Yes, it will help you avoid mismatched tags, and it will help you avoid sticking body text in a header, but it doesn't do very much else for you. I'm disappointed by much of the research around blocks. Too many people are taking on the easy problem of wrapping blocks around languages for new domains, rather than taking on the much harder problems that exist in this space. Compared to reasoning about program behavior, program syntax is easy. Today's popular block editors help with these easy problems, but not the hard ones. Here's an example of what I mean by this. The Snap toolkit built on Scratch to make an underlying language that is much more scheme-like. One can define functions, use closures, and more. And Snap has been combined with a fantastic curriculum to create really rich and friendly on-ramps into computer science. I think that's super cool. Some folks have even added to Snap to do things like add a parallel computing library, where you can use blocks to make shared buffers, locks, and pass data around right in your browser. And I think this is pretty amazing, but it also really bothers me. It's cool that we now have tools with easier syntax for working with shared buffers and the locks we need to manage them, but the hard part of parallel computing is not the syntax. It's the semantics. Blocks are not going to solve a race condition or prevent a deadlock or stop you from forgetting locks around your critical sections. And those are the problems that make parallel computing hard. The work on blocks will be much more interesting when we really harness the power of structure editors to help people to reason about programs. When we use these technological possibilities to assist people with the much bigger challenge of program semantics rather than just syntax. There's an irony here, of course. Tools like Blockly have made it easier than ever to build block editors, and so we're seeing more of them. But they've also made program editors more detached from compilers and runtimes than our IDEs were 2 decades ago. Through this detachment, we've pulled the editor away from the context where program text has meaning, and we've limited their potential to help users. There are 2 facets to the limitations of today's block editors. The first is the overwhelming emphasis on isomorphism, which limits expression. If your blocks can't have more meaning than the text that they're one-to-one with, then they're definitely not more expressively powerful than that text. The second is that detached editors limit the ability to support the semantics of programming. If your editor isn't linked to your compiler, it can't do all the things that it should to help you to reason about your program. Let me say a bit more about this. Because using tools like Blockly makes it hard to escape tying our block editors one-to-one to text, we can't actually make them more expressive than the text itself. And that's fine if your goal is for students to learn to write text. There are many researchers interested in transitions from blocks to text, but that's not so important to me. I care more for students designing and understanding interesting systems, and I want to give them powerful tools to do that. These are the harmony rules for classical chorales that I showed before. You can change one edge of this graph and get the blues. Writing this out with a block editor sucks. Yes, we can figure out how to compile this NFA down to imperative text, and then from there it's easy to imagine the blocks that would describe the program. A novice might start with something like this, but they would be wrong. So then we would have to teach students how to convert NFAs to DFAs or implement some sort of backtracking algorithm, and then figure out how to wrap blocks around whatever language they're going to use to program that. What I want to know is, how much should we prioritize learning to do that versus empowering computational expression through the most powerful way possible as early as possible? The graphical state machine in the top left is far richer than the text, and it directly corresponds to the abstractions that are native to the musical domain. We should leave them that way. But by tightly tying our graphical editors to textual languages, we're shortchanging users and learners by limiting their expression. The other point I made was about the detachment of editors and how they limit the support that can be provided for editing. The problem with interfaces like this is that they don't make hard problems easier. The hard thing about programming is understanding program behavior. If this editor was smart, it would not let me write code like this, or at least it would throw up big red flags. A smart editor would know that a divisor should never be allowed to be 0. Now you and I can see the problem right away if we're experienced programmers. We even know how to check for this sort of thing automatically at compile time, and can even do it with much more complex code than this. So why can't this editor? The reason it can't is because it's a one-way code generator. It doesn't care a whit for meaning. And I'm here to tell you that it should, and that there's surprising depth to how well it could, which I'll talk about more in a moment. This is the last part of my talk, and I'm going to talk about some design research suggestions for researchers on visual languages and human-centered computing. My 2 suggestions are that we start to develop editors that support what I'm calling representational hybridity, and that we imbue these editors with the power to do multi-scale program checking, from small local programs all the way up to distributed systems of programs. Here's what I mean by representational hybridity. We need editors for a world where CS is only semi-abstract. We need editors that enable programmers to work with and combine representations that are native to different domains and that have the most expressive power possible. Text as a least common denominator will only get us so far, and we can do better. I can certainly transform this decision tree into an if-else ladder, and then do that with blocks, but I can't really do that same transformation with a neural net. Instead, we need to develop programming editors that let us compose these just as they are, and to get beyond the limitations of text as a least common denominator, because it will not support that. Fortunately, there are techniques from functional programming that can really help us to make new kinds of very powerful editors. We can think about both the classifier on the left and the harmonizer state machine on the right as pure functions. Our classifier is a pure function, so it doesn't matter what its internal model is, a neural network, a support vector machine, k-nearest neighbor. The same is true of our harmonizer NFA. We can transform it into a DFA in text, or we can just leave it as an NFA, and use something like a list monad to handle the uncertainty about what state we're in and eventually find the right one. If we can represent each of these system elements as a pure function, then we can use a variety of techniques from graphical programming languages to combine them. In many cases, I think data flow is a more natural way to represent this, but people like blocks, so I'm going to go with that here today. Blocks and rich type systems can be made compatible with one another. And prior work on blocks-based editors has shown how we can generate new kinds of blocks that support the use of arbitrarily complex type systems, including something like a list monad. This work from the last Blocks and Beyond workshop shows how color can be used to represent Python's built-in types. And more recently, Lerner, Foster, and Griswold showed how shape and color can be combined to support types of pretty arbitrary complexity, and they've even built an implementation of this for Blockly. So clearly, we can think about the kinds of program components that we might be able to make as functions, and we can use blocks to represent functions that have rather complex types. But how do we use non-symbolic means to define new blocks that we can then combine with other blocks? Rebecca Fiebrink, Peter Norvig, and I ran a workshop this summer on research on learning about machine learning. And my favorite position paper submission was from a student intern at Microsoft Research. Majid built tools that let one record sensor logs from devices like the BBC Microbit, and then train a classifier which synthesizes new event handling blocks right inside the editor. You can then click on those generated blocks and edit their definitions by deleting training data or adding new data. Essentially, you're using interactive machine learning to define blocks right in place in a program. And the programs that you make are hybrids. Some elements are defined symbolically and logically, while others are defined statistically. That's what Majid managed to pull off in a single summer. I hope you all will pick up this mantle and explore the many opportunities that exist to create hybrid editors like Majid's. But even if you do that, it still won't be enough to make me happy. I want us to make headway on this problem as well. Not just this literal problem, but the problem of helping programmers to reason about the semantics of their programs that this problem reflects. And that brings me to my second suggestion for multi-scale program checking. As we move towards beginners constructing programs that have heterogeneous pieces, including distributed programs communicating over networks, we need editors that can provide more useful feedback to programmers. Research on compilers and formal verification is a goldmine for ideas about how we might go about doing that. For decades, dependent type systems have made it possible to create languages such that programs like this cannot compile. Dependent types let us specify properties of values or relationships between values right within a type system. We could say declaratively that the second operand of division must be a non-zero number. And if we do that, then this program has a type error. It can't crash because it can't be compiled. And if it can't be compiled, we can represent that and explain why right in an editor. Ben Schneiderman years ago wrote a set of golden rules for interface design. And number 5 is that interfaces should prevent errors, and that when they can't prevent them, they should detect errors and warn users. This editor is a failure as a user interface because it doesn't prevent this error, and it doesn't detect it, and it doesn't warn about it. The user is left to scratch their heads at runtime to figure out what went wrong. To solve this problem, we need editors that have the intelligence of state-of-the-art compilers. Now, I'm not a programming languages researcher per se, but as I've gotten to know the programming languages literature better, I've been amazed by what we're able to encode now right into type systems. We can cross levels of scale, from the composition of local programs all the way up to distributed systems. Session types let us bake network protocols into a type system. And this paper includes examples of how multi-phase protocols like this can be represented as types. Once this representation work happens, then programs can be verified to detect whether they communicate in the ways that they're supposed to. You might be thinking that this is all a little bit crazy. It might seem implausible that beginner programmers could actually write and check formal specs for their programs or protocols, but I don't think it's so crazy. And the reason why not is that We're already seeing students do this. 7th grade music students are already able to generate diagrams like this and use them to make harmonies, but also to check whether the harmonies that others have written are valid within their intended genres. If this state machine accepts your song, then it's a valid chorale. This is model checking. 7th graders can already do this for music. There's no reason they couldn't also do it for programs. Our academic brothers and sisters in the programming languages community are doing really cool work on structure editors that are smart about program editing processes, that can support the ultimate embedding of this kind of checking and verification right inside editing tools in user-friendly ways. The Hazelnut team has created a formal calculus for making smart, type-aware structure editors. This calculus represents the process of program construction and editing. It has a notion of a cursor and of incomplete programs where there are holes where code is missing, but where there may be some knowable constraints about what code could be written there. And then the system can provide real-time assistance with program editing. Given what we can do with dependent types and session types, this means that we could make much more semantically helpful block editors. Now, a challenge with the Hazelnut work is that it's mostly being done in the programming languages community and not within the human-computer interaction community. This isn't a criticism of them, but it's a realistic reflection of the differences between the PL research community and the world of HCI and education. The coin or the realm for PL is proof. And Hazelnut is a formal proof of concept on a very limited language. We need stronger collaborations between HCI researchers, learning researchers, and computer science education researchers, and the PL world so that we can start to understand how to bring work like Hazelnut from the realm of provable theory into empirical practice. Work like Hazelnut shows that we can make editors that help programmers to wrestle with the hard semantics of programming and not just the syntax. But we're going to need new collaborations between fields and with teams like Hazelnuts to bring this approach to life in our own research. These new kinds of editors could help people to build programs that combine classical symbolic programming with machine learning and to correctly build distributed systems out of distinct communicating programs. In conclusion, machine learning and distributed systems challenge our theories of what computer science and computational thinking are, and yet they can also be accessible to novices. But we need tools that help people, and especially learners, to wrestle with complex program semantics. Our current approaches to supporting this in block editing is too limited. We need to go beyond block text isomorphisms. And we need to embrace the ways in which type systems and functional programming could provide a very powerful theoretical basis for new kinds of editors. Thank you.